So in the last hour, we talked about mixing two continuous distributions. In particular, mixing two exponential random variables. And one of you asked, what happens when we mix discrete distributions, and also how do we recognize a mixture of two discrete distributions when we see the moment generating function. So here's an example that we can use to understand several of those. We can answer several of those questions with this example. Okay, suppose somebody gave us the following moment generating functions. Mx of s is equal to p over 2 plus e to the sp over 2 plus e to the 100s times 1/2. What do you think? First of all, is this moment generating function associated with a continuous or discrete random variable? Let's, in general, let's remember what the moment generating function of a discrete random variable looks like in general. So in general, mx of s is the expectation of e to the sx, which is found by a summation of e to the sk px of k, where px of k is the PMF of the discrete random variable. This is computed for all integer values of k, the summation. So in the summation, what kind of terms do we have? We have terms like e to the minus 2s times the probability that x is equal to negative 2 plus e to the negative s px of negative 1 plus e to the 0, which is 1, times px of 0. So the coefficient of the constant term, e to the 0 term, is px of 0. If you will, the DC component of the PMF. And further on, we can go like e to the s, px of 1, e to the s squared, px of 2, and so on like this. So basically, if somebody gives us a moment generating function that is in the form of e to the s terms together with coefficients, we can read off the PMF directly from these coefficients. Okay? In particular, corresponding to this PMF, okay, for the example, for mx of s equals p over 2 plus p over 2 e to the s plus 1/2 e to the 100s. What do the coefficients correspond to? This coefficient corresponds to the px of 0 term. This must be px of 0 because it comes with an e to the 0s. Right? This coefficient must be equal to px of 1 because it comes with e to the s times 1. And this coefficient, 1/2, must be px of what? 100, right. So can you tell me the PMF with this transform? So px of 0 is 1/2, sorry, p over 2. Px of 1 is p over 2, and px of 100 is 1/2. Maybe it doesn't make a lot of sense unless p is 1/2. So how about we make this also p over, we make this also 1 minus p. Huh? So let's change the example here. 1 minus p. How about that? So this would be 1 minus p. At least we want the PMF to add to 1, and the previous PMF added to 1 only if p was equal to 1 over 4. So, or sorry, 1 over 2. But anyway. Okay, so this is our PMF. And it's coming from a mixture as well. By the way, let's plot our PMF. This is k. This is px of k. So px of k is either 0 or 1. I mean, it takes non-zero values at 0 and 1 and 100. Okay, this is 1 minus p. This is p over 2, p over 2. No need for the parentheses. Okay? So can we write this as the mixture of two distributions? Yes, we can write this as the mixture of a Bernoulli random variable together with a constant, which is 100. So x is either Bernoulli with parameter p with probability 1/2, or it's exactly equal to the constant maybe we did this the other way. Let's write this first. X is equal to exactly 100 with probability what? 1 minus p. And with a total probability of p, it's either this or this. Okay? So with probability p, x is Bernoulli with parameter 1/2. Because given that x is Bernoulli, it takes the values 0 and 1 equally likely. It's equally likely to take 0 or 1. So x is Bernoulli with 1/2. Okay, with probability p, and x is equal to 100 with probability 1 minus p. So x is the mixture of a constant and a Bernoulli random variable. Okay, when do you have such a thing occurring? For example, they will, you will get a certain result from a test. It's not a midterm, okay? It's a different kind of test. So your score will either be 100, that is a certain result, or with probability p, and you can think of p as a large number if you want, close to 1. Your score will be determined between 0 or 1 by tossing a coin. Okay, so in that case you have this situation. Yeah? I don't know whether you can find a good example corresponding to this in real life. You probably can if you really think hard enough, but I hope you understand the example mathematically. Okay, so what have we done? We have gone from this description of the moment generating function to the PMF. What did we do? We just read off the values of the PMF, px of k values, from looking at the coefficients of the e to the sk terms. Here's our PMF. And further, we realize that it's a mixture of, we don't, you don't really need to express this as a mixture. But for the sake of giving it a correspondent to the exponential mixture, which is a mixture of two continuous distributions, I wanted to just give you a mixture of two maybe trivial discrete distributions. Any questions? Okay, so we reached our final application of the moment generating function, in other words, the transform, which is making sums of independent random variables easy to handle. So suppose x1, x2, up to x sub k are independent random variables, and we want the moment generating function of their sum, y, which is the sum of xi's, I from 1 to k. We'll just show that this moment generating function has a simple form. That's, again, we won't have to take any integrals. We'll exploit all the exercise we've done of expectations. So all the exercise with expectations is going to pay off here. Let's see. So I want my of s, moment generating function of y. This is the expectation of e to the sy by definition, which is the expectation of e to the s summation x sub I going from 1 to k. Any problems? I just wrote the definitions so far. Now what? I can break the summation here into a product of exponential functions, right? It's the expectation of the product I from 1 to k of e to the s x sub I. Any problem? Because the e to the s x1 plus x2 is nothing but e to the s x1 times e to the s x2. Any problem here? Okay. If you want, let's write it this the long way. This is the expectation of e to the s x1, e to the s x2, all the way up to e to the s xk. Now comes the big step. I have the expectation of the product of functions of x1 and x2 and xk. So this is expectation of f of x1 times f of x2 times f of xk. But the x sub i's are independent. Okay? Therefore, expectation of the product is equal to the product of expectations, because the random variables are given to be independent. Remember? So this becomes the product of expectations, e to the s x sub I from 1 to k. Any questions? Now the next step is to simply substitute in the definition of the moment generating function. This is mxi of s. So what have we shown? We have shown that whenever x1 up to xk is an independent sequence of random variables, independent, y of s, where y is the summation of xi's, I from 1 to k, is given by the product mx1 of s times mx2 of s times all the way up to mxk of s. We did not talk about PDFs or PMFs. This is general. So let me repeat, when you add independent random variables, you multiply their transforms. Addition in the random variable distribution domain, so addition of random variables corresponds to multiplication of transforms. Some of you may remember in the Laplace transforms, when you convolve two functions, this corresponds in the Laplace domain to the product of their Laplace transforms. Remember, when we add random variables, if they have PDFs, we are convolving their PDFs to get the PDF of the sum. The convolution in that domain corresponds to multiplication in the transform domain. Did that answer your question? What's your question again? No, these are not PDFs. Let me switch the letter to G. These are just functions. I just wanted to invoke our result, which says if you multiply the two functions of random variables where the random variables are independent, the expectation of the product is equal to the product of the expectations. So, yes. Okay, so that's another thing that makes life easy. Once you know the transform, rather than do convolution, you can simply multiply the transforms. Okay, so here's another application. This is going to be, so the next two examples are the last two examples of transforms we'll do today and in this class. But they're both important, and particularly this first one, sum of independent Poisson random variables, I would like you to pay a lot of attention to, because it's very related to merging Poisson processes. Poisson processes we'll cover in the last week of this course. Okay? So let's take two Poisson random variables. Well, first of all, do we remember the moment generating function for Poisson random variables? Remember? Can you remind me? So if x is Poisson with lambda 1, rate lambda 1, what is mx of s? E to the lambda times e to the s minus 1. Right. And let's also take y, which is Poisson, with another rate, lambda 2. My of s is equal to e to the lambda 2, e to the s minus 1. And we'll further assume that x and y are independent. So what do? We add them. Let z be x plus y. We add them. mz of s, the transform of the sum. We just showed that the transform of the sum is the product of the transforms. So mz of s must be equal to mx of s multiplied by my of s. In other words, e to the lambda 1 e to the s minus 1 times e to the lambda 2 e to the s minus 1. Now when you multiply out, you get e to the lambda 1 plus lambda 2 times e to the s minus 1. Do you recognize this? you recognize this, of course, as the moment generating function of a Poisson random variable with mean lambda 1 plus lambda 2. So we conclude that the sum of two independent Poissons at rates lambda 1 and lambda 2 is again a Poisson at rate lambda 1 plus lambda 2. This is a significant result. We use this all the time in, for example, queuing theory. It underlies a lot of assumptions we do in networking and in many other fields, including physics. Okay? So, any questions about this? Okay. And the final example, again with Gaussians. Okay. Gaussian distribution, the Gaussian distribution has a lot of important properties, a lot of nice properties. That's one of the reasons why the Gaussian distribution is used a lot in engineering, as in many other fields. So we saw that when you take a linear, when you linearly scale a Gaussian, you get a Gaussian. The next one shows that if you add two independent Gaussians, you get a Gaussian. But first of all, let me make sure that you notice the word independent here. For example, I'd like you to give me a counterexample showing that when you add two dependent Gaussian random variables, you can get something very different from a Gaussian. Take x, which is Gaussian. Now take y, which is very dependent on x, for example. Right, y could be, for example, how about y is negative x? Okay, and when you add the two, what do you get? You get 0. As in your example, if y is, for example, x plus, negative x plus a constant, when you add x and y, you get a constant, which is very different from a Gaussian. Okay? But the result is when you add two independent Gaussians, the result is also Gaussian. Let's do that. X is normal with mean mu variance sigma squared. And y is normal with mean, maybe call this mu 1 and sigma 1, mu 2, sigma 2 squared. So they are, x and y are independent. And z is x plus y. mz of s is mx of s multiplied by my of s. We computed at great effort mx of s, remember. What was it? E to the s mu plus sigma squared over 2s squared. That's mu 1, this is sigma 1. And the other one is e to the s mu 2 plus sigma 2 squared over 2s squared. Multiply the two. We have two polynomials in the exponents. Just need to add the polynomials. So basically add the coefficients with the same power. S mu 1 plus mu 2 plus sigma 1 squared plus sigma 2 squared over 2s. What is this? This is the moment generating function of a Poisson random variable. So Gaussian random variable. Z is Gaussian with mean mu 1 plus mu 2 and variance sigma 1 plus sigma 1 squared plus sigma 2 squared over 2. So what happened The means are added as, you know, intuitive. And the variances, oh, there's no 2. The variances are also added. Okay. Any questions? So that concludes our discussion of transforms. The next chapter, the next topic, which we'll cover next week, is limit theorems. So I'll see you next week.